So despite being a very avid Spark user, today's demo, which admittedly depends on the Wi-Fi working, so we may skip the demo, but we'll at least try it, actually runs on top of Apache Flink rather than Apache Spark. Are there any Apache Flink users? Okay, less than I would expect for Berlin, but that's totally fine. You pretty much covered all of this. The only thing which is maybe different is I've started doing some code review live streams, and you're not in the contributing to open source talk, but if you are interested in sort of seeing how a large project like Apache Spark does its code reviews, you can watch these live streams, and hopefully it makes our GitHub comments a little more personal. And I've worked at a bunch of places. They're all nice. They all paid me money. I've written several books. High Performance Spark is the new book. It is probably not relevant for this audience particularly, but that should not stop you from buying it. The royalties on it are much higher than the other one. So if you have a corporate credit card, it's a great way to give me money. In addition to who I am professionally, I'm trans, queer, Canadian. I work in America on a work visa that they're debating taking away, which is lots of fun and part of the leather community. And this is not particularly relevant to training machine learning models, but I think it is useful to remember that we all come from different backgrounds, and we should try and be inclusive of people. Otherwise, we're just going to build really shitty models and reinforce our existing stereotypes and biases, and everything will go to shit, and it'll be our fault. And I don't want it to be my fault, so don't do that. Okay, so hopefully you're nice people. If you mind pictures of cats, this is not the talk for you. And you don't have to be familiar with Spark or Beam. I'll talk about them in detail. So TensorFlow on Spark with Apache Arrow is demo number 2. That demo can sort of run locally sometimes. I have Python and Go on Beam. The Go prototype works slightly more reliably because it does less things. But the fun feature prep stuff is all in Python. But I want to be clear, the stuff that I'm going to show you today is not ready for production use. Do not use this in production. It will go poorly. To reinforce that, really don't use this in production. It will go really poorly. I probably should have updated that to June 8th. I made the slide yesterday, but you get the idea. This will not, for the wonderful folks listening on the recording, necessarily be true indefinitely. Hopefully we do fix our undocumented features. But, check before you run this for real. So I'm going to talk about how we enable non-JVM support in Beam. This is important because TensorFlow and a lot of the cool stuff that we want to do is in Python, but Beam itself is written in Java. I will try and show you a TF transform demo. Failing that, we can go through the log files of a demo, which I ran when the Wi-Fi was working a little better.
The Wi-Fi will work.
Okay.
Connect to Beholden.
Okay, I'm going to apparently connect to a different Wi-Fi network for the demo, and please don't all connect to that same Wi-Fi network. Anyways, and if there's time, there's some other things that I can go into that are pretty fun too, in my opinion. So why do we need to do this, right? If you listen to perhaps some deep learning talks, you're like, oh, it's magic. I just put TensorFlow on my data, and out will come venture capital money and, insights. And that's certainly half true in San Francisco. You can slap deep learning on pretty much anything and receive venture capital. But even if you're, doing mnist.csv, you probably need to do some form of feature prep. And there's a really good chance that if you're actually a good use case for deep learning, your data probably doesn't fit on a single machine. If it does, there's a chance that you may not be a great use case for deep learning. And so even if you want to raise some VC money, it's better if you have a large proprietary data set, and it's better if your software works. It's a lot easier to, get them to give you money when your stuff works. And to do that, we have to transform our raw features into kind of useful things. And so TensorFlow on its own doesn't have a lot of really awesome tools for feature prep, but there's a bunch of cool tools built around TensorFlow in the ecosystem to do feature prep in a way that we can also do this at serving time. TF Transform and TFMA and TF Serving work together. There's a wonderful package called Kubeflow. It doesn't work with any of the things I'm showing you today, but it might in the future. And the alternative to this is to write giant piles of custom Python code to do our feature prep, doing things like computing the mean over some data and computing z-scores and all kinds of fun things. However, you probably don't want to spend your time writing distributed algorithms to compute these things because it's not a lot of fun, right? We'd much rather use a tool which can do this for us, an open source tool, of course. And the other problem with the giant pile of custom code is once we've done that, we also have to recreate it at serving time. So if I write a bunch of custom code to do my feature prep, I then have to write a bunch of custom code to take my incoming features from people that I'm trying to predict on and transform them so that I can actually feed it to TensorFlow. And this often results in copy pasta code, which is really great for job security, except when you forget to update your copy and paste code and you start predicting really bad things. I say this as someone who has definitely not done that at this job, but I've had a lot of other jobs. So traditionally, you write a custom feature prep in your favorite big data tool. Mine is Apache Spark, but maybe yours is Apache Beam or Dask or something like this. You run it on you train on your prepared data, and then you go into model serving, and you're like, oh, yeah, okay, I guess I need to transform everything. And you do this, and it's error-prone and sad. So yeah. But the magic will save us. Yay! So TF Transform is kind of cool. It allows us to preprocess our data in a number of ways, and it also integrates nicely into the existing TensorFlow model serving tools. It's open source. It's not perfect, and please do not use this in production unless you happen to be running on GCP with Dataflow. This on top of Flink, which is what we're going to talk about today, is garbage, but getting better. Okay, so what does this look like? Our very fancy feature prep stage, we might want to center some features, scale some things into a 0-1 range, encode strings to integers, all kinds of exciting things. Code that you probably could write very easily, but there's no real reason for you to bother writing it. And what happens is we can take this, and TF Transform will fit all of these things and produce constant tensors. And so it does a full pass over our training data and produces constant transformations, which are then used at serving time. So take thing, add data, receive magic. Yay! Okay, and there's a whole bunch of other things that we can do in there too. Everyone loves n-grams. We can pretend that that's a great way of handling text. It does not integrate with Spacey today. It probably should, but there's lots of fun things that we can do inside of here, and you can add more things into it. It's just a pain in the ass. Okay, yeah. So how do we get this to work? TF Transform is written in Python, but Beam, which is the layer it runs on top of, is written in Java. And the TLDR is we use gRPC and protobuf. That's not particularly important, but essentially you can think of it as we just copy data around a lot. And if you're a traditional big data user, that might not be so surprising. But if you're coming from maybe more of an HPC background, you might be like, why are you copying these buffers all of the time? And it's because formats are hard. Also, apparently, so is Python 3. We still require Python 2.7. But if anyone wants to come and have the delightful, if you missed out on the experience of modernizing a Python 2.7 project because you were, in grad school or something, you can come and join us and relive that wonderful experience and help us modernize a delightful code base. And it's getting there. There's a bunch of people working on making it work with Python 3, and we will probably finish it within the year and a half. Like, probably. Okay, so how does this work? We have this portability framework which allows arbitrary execution to happen. And this essentially spins up Docker containers and does IPC into the Docker containers. And this is nice because if you're coming from the Spark world, you have this wonderful thing where it tends to spin up Python directly on the metal, and then you have whichever Python happens to be installed on that machine with whatever libraries happen to be installed on that machine. And that tends to go poorly, especially for people who are trying to use things like TensorFlow, where you really want to have nice compiled versions. There are a bunch of opportunities for improvement here, I believe is what it would say in the performance review for Beam. And right now, essentially, you have to put your permissions inside of your Docker file, which is not good, but we'll fix that for sure. Okay, so what does this quality design look like? We have our magic portability layer, and Python can talk to us, and so can Go. Are there any Go users in the audience today? Ooh, I have a demo for 2 people. And Java, of course, talks to us. Beam is the common SDK, and it can compile down essentially into running on top of Google Cloud's Dataflow. And recently, it finally started working. It can run on top of Flink, which is cool because then you don't have to give me money. You can just use open source software and not be locked in. And in the future, we're totally probably going to support Spark, but right now the main thing that we support in Spark is segfaults. So working on that. So how does this all relate to TensorFlow? TensorFlow is in Python, kind of. It actually calls a bunch of native code. And once we finish this SDK, you can use this easily in practice. We can use it today with a lot of pain. And in theory, we can reuse our data prep code more easily. The only catch is if you have some really custom business logic inside of your data prep, that's going to be kind of annoying for us to get to work. Ooh, so we're going to pick an example. The Chicago taxi data example is the one which runs. The other example crashes. And so this is the example that we're going to try and run. It does a bunch of string to int and bucketizing and some z-score transformations on our wonderful data. And so we're going to try and run this. And based on my testing yesterday, there's a 1 in 3 chance that this will be an excellent opportunity for me to reboot and do Q&A when it crashes. I'm hoping that's not the case today. And to be clear, this is a fork of a fork of a fork running on top of a master branch of some software. None of this stuff is released. You can totally go and do this yourself, but if you do, good luck. Okay, cool. So I have my job server running. Let's see if let's see if I can talk to the internet. Ping google.com. Okay. That looks great. Sure. Maybe it'll work. So we're going to run this pre-process. Oh, I'm on this one. Yeah, that's okay. Glorious employer provides. Oh, it's recorded. Hi, boss. Anyways, so we're gonna start. Actually, let's not put. Ooh, fuck. Okay. Let's go tail-f, F4. And okay, so it is running preprocess.py, which is that wonderful Python code I just showed you. Ignore the deprecation warnings. They were just there for to keep it exciting. And it's kicked off the job, I think, maybe. No, it hasn't kicked off the job. That's not good. Okay. Ooh. Okay, cool. Let's run this without redirecting it. Yay! Okay. So yeah, it reads and writes from a Google Cloud Storage bucket. It does this because I don't have HDFS running on my local node, and this is the part which requires the internet, unfortunately. Ignore the CPU instruction warning. That's also just to keep it exciting. And we can see it's creating its sort of initial graph. This part normally finishes faster. Okay. Oh, yay! Okay, so it's done its first part. It's written out some temporary models, and this just is the model without them being fit. So it doesn't have the constant tensors yet. It's the tensors which reference the transformations which are going to happen. Yeah. So this is really exciting to watch, for sure. And soon it will kick off a beam job. However, this might be a demo that we... Ooh, okay. No, it's not going to do anything yet. Okay, this can be a demo that we return to ooh, okay. It's sorry. I have that optimism that's required to be a programmer where you're like, well, maybe this time, right? And eventually it's true, and you remember that one time that it worked, and that's what keeps you going. Especially when you work on high-quality open-source software in Python 2.7. Okay.
Can you give some advice to those of us that get criticized for still using Python 2.7?
So the question is, do I have some advice for people who get criticized for still using Python 2.7? And I would say appeal to authority and claim that Google still uses Python 2.7, therefore it's okay for you. This is clearly a bad idea, but assuming the person you wish to convince of your terrible idea is not in this room, they might believe you. The alternative is you should stop using Python 2.7 because it's painful. So what's happening now is while the Docker files have all of the dependencies that we want installed in them, it doesn't have our job inside of it. So it's taking all of the sort of Python code for our job and packaging it up into a tar file and shipping it across to our good friend, the job server, who has started running. Yay! Oh, thank God. Okay, that was going to be super awkward. And we can see it's actually, it did its string to int, so it did its string to int conversion. It did the scale to z-score transformation. We can read this log and see all kinds of fun things that it's done on our data. There's a bug where I don't get standard out in the other process all of the time. So everyone loves reading log files emitted by a Java process. They're notoriously not verbose. And so anyways, we can see that it's done what we've asked it to do, and that's kind of cool. And while we could wait for it to save the resulting model back to GS, while the timer is no longer running on this screen, I suspect that might take a while based on the Wi-Fi. So we're going to transition away from this demo, which is definitely not crashed yet. Keep going. Okay, cool. Oh, I took out the Go demo. I'm so sorry. If the 2 Go users in the audience want to come find me later, I am wearing a pink dinosaur dress and can show you a demo of something similar in Go. So now that you've done this, right, you've fit your happy TFMA model, how do we make this work? So if you want to use TensorFlow serving or any of the built-in tools, the nice thing is this outputted proper TensorFlow, so you can just use it with TF serving. If you've written your own high-quality custom serving layer, you have an exciting opportunity to re-implement a bunch of code. There's a guide that goes into a lot more detail than this demo did, and the slides. It's not focused on running on open source, but if you change all of the places where it says data flow to Flink, it kind of runs. And so you can't see the link. I will post the slides to my Twitter, and then you can click on this link, because I should have put the link text here. And my Twitter is Holden Caro, and the slides will be there. Okay. Optional second Beam demo time. Who wants to hang around for 5 minutes while we run word count? Cool. I'm sorry. We're going to skip demo number 2 and just roll with it. Okay. So sometimes when I talk to people about how stuff like this works, they're like, wow, that's a really terrible design, Holden. I should not use this software. What should I use instead? And I want to assure you, everything else is garbage too. Different trade-offs, possibly better for you, possibly not. Let's look at some of the other things that we do to accomplish similar tasks of running Python code in big data ecosystem. How many PySpark users are in the audience? Okay. Keep your hands up if your PySpark code, if your PySpark error messages make sense. Is there anyone? Okay. Oh, 1 person. Good luck. I hope that keeps working. And so PySpark doesn't use gRPC and protobuf. It uses different things. We use pickling, sockets, pipes, and JSON. And I don't have a funny image for JSON. JSON's not funny, but at least it's not XML. So we can run similar things. Ooh, I have the timer back. That's wonderful. So PySpark also allows us to run Python code, and we can run similar things on top of PySpark. In addition, it's the same technique used for supporting other languages on Spark, just as in Beam, where Go is supported. They just pick different languages to bother supporting. It's fairly mature. It has a lot of performance hurdles from the design. I want to assure you we have fixed none of those in Beam. So it doesn't get any better. But we did fix some of the dependency issues, so that's cool. And this high-quality design looks like Python talking to Java, talking to Java, talking to Python. And you can really feel this when you get an exception. You'll get a Python stack trace wrapped in a Java stack trace, wrapped in a Java stack trace, wrapped in a Python stack trace. And you may get 2 times the number of workers that you have copies of that stack trace. Yay! So yeah, if that demo had failed, thankfully I'm running it on 1 worker, my laptop, we would have only gotten 1 error message. But if I was running it on a real cluster, I would have gotten hundreds. I'm not sure that helps. And Flink follows the same pattern. And so we can see that pretty much everyone was just like, wow, that looks like a good idea. Let's copy that without thinking about it. And we've excitingly recreated the same mistakes for about 10 years in a row. And so everything gets kind of more expensive. The error messages make no sense. And dependency management really doesn't work in PySpark, unfortunately. Thankfully, this is one of the things that we fixed in Beam. We were like, oh, the one example that I want to run is TensorFlow, and my machines don't have TensorFlow installed on them. I should fix that. And so it lets you have this nice Docker file, and you just install all of your dependencies. And I forgot to use the nice compiled version of TensorFlow, but you totally could use versions which are targeted for your machines. And all of the other things are less important, which is why they're not colored in red. And yes, we can also run TensorFlow on Spark. Yay! Yeah, we can run MNIST. Ooh. Or as I like to call it, the hello world of big data. Sorry, no, it is the hello world of TensorFlow, which is the word count of big data. And so, yes, yay, okay. So surprisingly, this actually works. Like there's a whole pile of code that is hidden behind the scenes, but this is the part of code that you would have to write yourself. If you run this, you might be like, wow, this is kind of slow. I wonder if it's going to get better. And the answer is kind of. And Apache Arrow is a really cool project which supports a whole bunch of different platforms, including CUDA, but more importantly for us, including the JVM and Python. And it gives us a consistent data format that we can actually share between each other rather than rewriting our data into different formats every time we have to switch between one of these systems. And actually, so some of the performance work that people were doing in Spark showed that for some jobs, we actually spend more time changing the data between formats than the actual work. And especially if you're computing relatively simple things like means and z-scalar transforms, you're going to spend more of your time just serializing data into different formats. And so, the PDF version of these slides, this isn't animated, but the galaxies here are supposed to be going by really quickly, like data moving really quickly. So this is a really well thought out one, so just pretend that this is animated. Or look at the slides later. Okay, and there's this vendor benchmark from a vendor that I no longer work for that implies this could be 242 times faster. Oh my God, that is a lie. Sorry, this is recorded. By a lie, what I meant is careful selection of facts. And yes, it could be 242 times faster under very, very specific circumstances. More likely, you might see a 50% speed up. That's nowhere near 242 times, but that's still pretty good. 50% is worth rewriting my code into a way that I can't understand anymore. And so this is the arrow diagram, kind of. And we can see Java and Python and R and even CUDA can talk to it. And it can also talk to data formats. So it can read in Parquet files. And if you want to just entirely skip Spark or Beam, you could, provided that your data fit in memory, at which point you probably don't need big data. You should probably get your data out of Parquet and saved into a local format that's useful. But I'm not telling you your data is not big. I know people get very upset about that. You've already bought your cluster, so we can just ignore that part for now. So how do we rewrite our code to use this? So Spark catalog register function, adding numbers. This is definitely a thing that we want to do in Python because numeric computation in Java. So definitely adding integers. This is the place to do it. And we use pandas UDF, and this looks pretty similar, right? Admittedly, this example was picked so that it looked really similar, but this is promising. And we can actually do this inside of TensorFlow on Spark. The main magic that happens is this really sort of gnarly for each partition. And we're going to rewrite this to use the new happy arrow path rather than the old RDD path. And so what we do is our doTrain function becomes a pandas UDF that returns integers because we forgot to support returning null. And so we would just return a lot of zeros. We'll fix that later. And the sad hack for now is probably the one part of the code which will survive. just based on my personal experience. And we just put our map function inside of here, and we call train function. This is really simple relative to the complexity of making TF on Spark work. Just hacking in support for the pandas UDF is pretty, by pandas UDF I mean Arrow. We call them pandas UDFs because the objects that you interact with in PySpark look like pandas data frames, or series, as the case may be. And so we get our data across the wire a lot faster. And now this looks like this. Yay! Java to Arrow to Python. That's a TensorFlow, kind of. And by kind of, I mean provided that your cluster has no nodes crash while it's doing this step, it's totally fine. And if it crashes, just try again. So it's that while try catch, just wait for this code to work thing. And that's because the scheduler in Spark makes some assumptions, and TensorFlow makes some assumptions, and those assumptions are very different. And we're working on fixing that, but it's probably not going to happen in time for you to run this code. So definitely, try, catch, and except. I spent too much time in Java land. I'm very sorry. And then just wait for the code to succeed. So there's some things that we could do. We could avoid copying this data into Python. We could set up our graph in Python and then just copy the data directly from the JVM into TensorFlow. And that would give us some cool performance benefits. The downside is I would have to write a lot of Java code, or someone here could write a lot of Java code. If there's any closet Java developers in the audience, just come talk to me. I have a bunch of cool projects for you to do that I don't want to. And you can fix this to go even faster. There's a whole bunch of references. If you're, here are the links that I was talking about earlier. You can look at the example guide. If you want to go play with Apache Beam and check out the master example and try and use this on your own data, you can totally do that. If you're more of a Spark user and you want to use TensorFlow on Spark, that's the version there, and you can do the hacks that I showed you earlier. And there's a whole bunch of other fun things. And I have 2 minutes and 49 seconds, so I'm going to say, okay, thanks, bye. Let's see if the demo finished. Let's not. Okay. Yeah. Does anyone have questions for me? Or I also have bonus slides. If anyone really loves slides, we can go look at more slides.
Questions? I'm sure someone is... Yes.
So thanks for the great... Is this on? Yeah, okay. Thanks for the great talk. I was wondering, is any of these things better with Dask? Because it seems like having the extra Java layer makes it, a little bit more difficult in some ways.
That is perhaps what one could describe as an understatement. And yeah, the extra layer of Java just doesn't add a lot, except for stack traces. I mean, so more seriously, the main thing that Java adds in these cases is the ability to interact with the rest of the big data ecosystem. So if I want to pull my data out of Hive, if I want to run on top of Yarn, if I want to be scheduled against some other things, it's kind of useful. But yeah, if you have a pure Python thing that only needs to interact with other Python things, Dask is probably a lot less painful. Sorry, recording people. But yeah.
More questions from others? I might can I ask a really noob question? When does it make sense to start using, these sophisticated technologies rather than just running on my local machine and kind of waiting for days until stuff works? That's totally not something I do.
Yes. Okay. So I see that there is sarcasm in Germany as well, so that's lovely. Yes, I would say at the point that you're waiting for days is probably an excellent opportunity to parallelize your work. Really, I personally do the cutover at the point that my data no longer fits in memory, or it takes like more than the amount of time I think I'm going to spend debugging the distributed system to run, which is because I'm an optimist. I'm like, most an hour to debug my distributed problems. It's never the case, but if it's taking like a whole afternoon, I think that's a good opportunity to rewrite your code. Normally, it's not too gnarly to rewrite on top of a distributed system, and if it is, just buy a bigger computer, or rent one from Google Cloud.
Quantum One, maybe.
Maybe.
That's the plan, anyway.
I don't keep up to date with our product announcements. But definitely, I'm sure whatever we sell is great, and you should buy it.
Good. More questions? Okay, so Morgan, thank you so much.
Oh, no, thank you.